Okay, good morning to you guys. So today we're going to be talking about another topic, and it's called the process management, not the processor management. Hopefully we're finished with the processor management and you know how it's managed. So the process management involves managing multiple processes that are running simultaneously. Or, okay, thank you guys. Or solving the problems that are caused by multiple processes running simultaneously in parallel. So we're going to face a number of problems when you have many programs working together simultaneously and sometimes accessing the same resources. So if you have a number of resources that are needed by multiple programs, these resources are also scheduled in a way that can cause many problems. So one of the problems we'll talk about is called the race problem. And we also have another problem called the deadlock. And finally, we'll have another problem, as well as the critical regions, critical sections or critical regions of code. And then we have issues with devices that are non-shareable or dedicated devices. Dedicated, anybody remembers what a dedicated device is? Or what is a dedicated device? Or a shareable device, the opposite of shareable device? What do you think is a shareable device? What does a shareable device mean? Anything? Anything comes to your mind? What's a shareable device? What's a shareable resource? If you guys have a device, a calculator, for example, would this normally, would you? Calculator. Imagine if this was a calculator and we all need to use it. Is it a shareable device or is it a dedicated device? Shareable. Shareable. Very good. It's a good answer, but it's the wrong answer. Because few people cannot simultaneously use it at the same time. If a device can be used simultaneously by more than one user, then we can call it a shareable device. But if I need to use this calculator and you also need to use it, one of us has to wait. And that's a dedicated device. A device that can only be used by one user at any given time. Don't forget, don't just say a device that can only be used by one user. That's not a good definition. It can only be used by one user at a time, but it can be used by many users, but not at the same time. Okay, so that's really the main difference between a dedicated device and a shareable device. And because we have dedicated devices that if we both need to use them, let's say I need to use a printer and you need to use it. One of us only can use a printer. We can't both print simultaneously on a printer, or else, we'll get rubbish on the printer. We get a lot of, I want to print a letter and you want to print a report. If we both print simultaneously, it doesn't really come up successful. So that's why a printer is, by its nature, it's a dedicated device. And only one user can use it at a time. Don't forget, at a time. What's the consequence of that? If two of us need to use a printer, then one of us has to wait. this waiting problem. This is the issue, is waiting. And then if we have another file, we both need to use the file, then also one of us has to wait. And if we both need both, each one of us, you need the file and the printer, and I need the file and the printer. And if I get the printer, but you get the file, you have to wait for me to finish with the printer. But I'm not going to finish because I need that file that you have, and you're waiting for me to finish with the printer. So we could end up, both of us, waiting for forever, basically, because I will not give up the printer until I finish, and I'm not going to finish until I get the file. You have the file, and you're waiting. And if you're waiting for me, or I'm waiting for you, you're not going to finish either, because you have the file, but you need the printer in order to finish. And I have the printer, and we both are in waiting states, or sleeping states, waiting on each other, and none of us will finish. And that's what we call a deadlock. So these are the 4 problems that we'll discuss today and Friday. Right, so I'm going to start with the race problem. The race problem is also caused by multiple processes going for the same resource. And by the way, you don't get an error. As far as the system, the operating system, the computer, everything is running smooth, but it's not running correct. That's the problem. So let's look at the race problem. The race problem happens when you're updating files. At least this is a good example. Imagine if you have a bank account. You have a bank account and there's a certain amount of money in it. Let's say you have 1,000 euros. Okay? And now you received a check and you have 2,000 euros to add. You have a check, somebody sent you a check, pay Tom 1,000 euros. But also you have cash, 1,000 euros. So hopefully you're going to lodge the cash in your account, you're going to lodge that check into your account, and at the end you should get, hopefully, your balance should be, anybody knows what your balance should be? 3,000. That's what we are expecting, if everything goes smooth. But when computers started running in banks, sometimes they started noticing the following problem. Your balance is less than 3,000. So what happened? And it took a little while, and then they realized what's happening. And this is what happens. But remember, just want to remind you of something. When you're writing a program, as you should be writing programs by now, in order to change a value, if I said I have a file and it has a certain amount of money, let's say 100 euros or a number, I want to increase that number by 50, for example. I want to add 50. What do? In your program, first you say, open that file and read me that value. So read the value. So you put that value in X. X equals, and you read that number. So now we know what's in the file, what's in the record. So this is how you'd actually write a program if you're to update a file. First you say, get me the existing, the present value. So you read from the file the present value. And now modify this value. Now we're going to add 50 to this value. So you say X equals X plus 50, or whatever the value is. Now we have the new value in X. We say write. So you need 2 instructions, or at least. Read the existing value, modify it in memory, and write it from memory back to the file, the new value. So the new value is written and becomes 150. That's how you'd update a file. Any record, any value, you need to read the existing, add to it, or reduce, or whatever you want to do. That's how you update any record in any file. Now, let's go back to the bank. The bank also has a big file on a hard disk with your balance. But your balance at the bank at the moment is 1,000 euros. And just sitting there. That's the present value. Now, somebody gave you a check, you lodged it into the bank maybe this morning or yesterday. So today there's a bank worker who's sitting at the terminal and he's trying to insert that €1,000 into your balance. At the same time, you walked in with cash to the cashier at the bank and you think, can I lodge this? So there are two people or two programs or two processes working. This is the cashier and this is another staff member at the bank. And they want to add, each one of them wants to add €1,000 to your account. So this is what happens. This guy is running the program. Possibly the same programs, multiple copies of the same program. So this one gets to the point and say, read me, but they're doing it almost at the same time. Almost, not exactly, even not necessarily exactly at the same time, but almost within a second of each other, or way less than a second. So this guy says, get me the present value, get me the value now. How much do we have? So a read goes to the request to read that value, and reads that value and gets €1,000. So this guy is told, hey, the balance now is €1,000. This also guy here says, same thing. They say, I'm going to add €1,000 to that balance, read me the present value, or the balance. So sends a request to the file, and the file comes back and they say, hey, the present balance is 1,000. So those two programs are running simultaneously. So this guy here says, oh, you're lodging, you're sitting in front of this guy. You say, oh, how much are you lodging? So he counts it and say, add €1,000 to this value, so X equal 1,000, add 1,000 to X, so now X should equal €2,000. Similarly, the other application as well here, this guy says, oh, I got the now balance, put the balance in X, now I'm going to add to it whatever is in this check. And this check has 1,000, so add to X €1,000, so now X equals 2,000. And this guy, in his machine, X equals 2,000. Now, this what happens now. This guy says, write this new balance to the file. Whoever writes first, now the balance became 2,000. This guy comes in here now, says, no, write the balance to this value, write 2,000. So it overwrites that 2,000. They both have done their successfully written to the file, and as you can see, now the new balance is 2,000, which is wrong. It should be 3,000. So that problem started happening. This is many years ago. And they realized, oh, these things are, eventually they found out that, oh, one is overwriting the other. It doesn't always happen. It was very difficult to isolate it and know exactly what was happening, but this what was happening at the time. So, and this is called the race problem. They call it the race problem because these two processes, or three, are racing to update that record. And the one that writes the last, that's the value that's going to be. So the last process, the last value written to the file, that's the new balance, and that is wrong. So how did they solve this problem? This one problem. They solved it very easily. They solved it through a locking mechanism. They started using locks. They say, if you want to use a file like this, where things can really go wrong, see, writing to a file, you should never have it, everybody can write to a file. Even though the actual writing at that moment, only one can write, but still, don't get two processes or more trying to write at the same time without any control. That's what happens. And the control is going to be the lock. And the lock is what they introduce this in all databases. If you're a programmer, you might have to do it as well. It's probably the mechanism is already there, it's just requested. Or sometimes some operating systems automatically, when you say I want to write to a file, they say, okay, we'll have it locked for you. The way it works is that if a user asks for a file, they put a lock on that file. So if another user comes in, they don't even allow them to read from that file. So you want to read the balance? So how does the lock work? Let's go through the process again. You have a question? You put your hand up and I'll answer if you like. Okay, let's go through this, but now with the lock. You see how the locking mechanism works. So, these two guys start simultaneously. One of them is going to send the get balance, read first. So, this guy comes in. Is the file locked? No, it's not. It's free. So, it's given to this guy, and we put a lock in it. This guy says, I'm going to update that balance. So first I want to read that. So the moment it says I want to update something, we say, okay, we'll put the block. Imagine this is user A, this is user B. So now user B has placed a lock, or a block was placed by the operating system for user B. Only user B can use this file for the next second or two. It might be only a quarter of a second or 1/100th of a second. So now at the same time this guy sends a request and finds it's locked. So you put in a queue. User A, you are waiting, you have to wait. So user A is not sent the request, read the request, but it's not read. The operating system will delay it for maybe a quarter of a second or 1/100th of a second or even less. But this information now is sent to user B. There you are, I say the balance equals 2,000 euros. This guy is waiting. It's just sent the request. He's not getting any balance yet. It's delayed, basically. Now, this guy says, add to it 1,000. Now, the new balance is 3,000. Write this. So now, sorry, is it? What am I talking about? That's what we started originally. We said the balance was 1,000. And we want to add to it 1,000 from here and 1,000 from this user. So 1,000 plus 1,000 is 2,000. So this user now says, write 2,000 to the file, and you finished, yeah, I'm finished with the file, well then release the lock. So when the lock is released, A is requesting it. So the operating system will put the lock again, but now it's for A. That was waiting to read. Now, only now, the operating system will do the read. So the read comes in and say, oh, your balance is 2,000. So now this guy says, add 1,000 to it, and that becomes 3,000, write to the file. The moment you say close the file, you say, okay, the lock is removed, and it's available for anybody else after writing the new balance. So this way, by locking the file, you don't allow a user to read, and then another user comes to read, and then this guy writes and this guy writes. If you say, I want to change this file, it's locked for you. You read, you write, you close the file, and then we release the lock. We give it to another user. We don't allow two users trying to update simultaneously, and they both get it. So this is the locking mechanism. Very simple. The locking mechanism can be just a bit. Not even a byte, a bit, 1 or 0 for this file. If it's 0, it's not locked. If it's 1, the lock is on. You can't. We will delay you until it becomes available. Now, the lock mechanism works perfect to solve that problem, but it causes another problem. Remember the deadlock. If I need 2 files, and you need 2 files, I get one and you get one, I need the second one, you have it locked. I have to wait. You need the file that I have it, it's not free, then you have to wait. And we both end up waiting. I'm waiting on you to release the second file, and you're waiting on me to release the first file. And we're both stuck in a deadlock. So that's, you should be able to explain the race problem. If you're asked what's the race problem, you should be able to explain the lock mechanism, how the lock solves this problem. Now, the second issue, I said it's called the dedicated devices and the shareable devices. So who can remind me what's a shareable device and what's a dedicated device? Are you with us? No? What's the dedicated device?
The device is it depends on a particular thing.
Okay, that's a good definition, but it's not the right definition. What's a dedicated device?
A device that can be used by one user
at a time. It's a device that can only be used by one user at a time. That's called a dedicated device. And what's a shareable device? You know what a shareable device is?
The device can be used by so many users.
Very good. But it's not the right answer. What's a shareable device?
It can be used by multiple users simultaneously.
Simultaneously. You're missing that last word. At the same time. Don't forget, at the same time. Your definition will get you a zero unless, if you forget to put the word at the same time or the word simultaneously. It makes a lot of difference. And don't say the dedicated device can be used by one user. No. A printer is a dedicated device. It can be used by thousands of users, but not at the same time. Okay? So a dedicated device, the device can be used by only one user at any time. The shareable device can be used by more than one user at the same time. Yeah. So if we have shareable devices, I never have to wait. You never have to wait. If the device is shareable, let's say we have a TV in the room, and there's 10 of us. And if you want to watch the TV, there's only one channel, right? There's no remote. So there's one TV station. But anybody can come and watch simultaneously. We can all watch it and get the use out of the TV. So the TV is a shareable device. But, say, a calculator, no, only one user can use it. If we both try to put our formulas or calculations in a calculator at the same time, 3 of us, it's not going to work. So only one user should use it at a time. But once the first user finished, they can give it to the second user. So many users can use it, but not simultaneously. Now that leads us to this problem that called deadlock. So a deadlock is basically, it only happens if the devices are dedicated. That means, and there's waiting involved. And more users are running simultaneously and they're trying to get those resources. And there's also more than one resource in the system. So, the example, we'll have an example. You need to print a report and I need to print a report. You need to write a program to read information from a file and send it to the printer. I'm creating a report to print the students' names. You're also creating a report that uses the same file. You want to read the file, but only print the students that passed the exam. They're 2 different reports, but they both need the same file and the same printer. So we have a file on this side with all the students' names, and we have a printer device that will print that list. And is user number 1, person 1, and person number 2. They're 2 people, or persons, or programs, or processes. So P is for a process. Now, both these processes, they want this particular file. There are many other files, but they only want this particular file that has the information they both need. So this guy would like to open this file and read it and send the information to the printer. Same as this one. He wants to open this file, read it, and send the information to the printer. But if this guy gets the file, and this guy gets the printer, see, this file now belongs to that guy, and that printer now belongs to the second user, Now, this user says, okay, I got the file, I read the information, now I need the printer. Can I have the printer? No, because it's already given to someone else. It's already allocated. The word used is allocated. See, there is even a language in reading this diagram. That's something you have to get used to or learn. You see an arrow, you always name from the tail of the arrow first, and name then followed by the front of the arrow, the head of the arrow. You say the printer is allocated to process 2. That's the way it should be read. Okay, what about this one? What do we say here? This file is allocated. This is the word to use. You must remember this word. So the file is allocated to process 1 and the printer is allocated to process 2. That's how it's read. Also, when you're requesting you say person 1 is requesting the printer. So anytime a process or a person is pointing at something, it's like, I want that thing. Like if there's a calculator, say, can I have that calculator? That's requesting. If the arrow going from the calculator to the person, we say the calculator is allocated. See these two words? If you're going from a person or a process pointing at a device, that means that process wants that device. If this device is allocated to this person, that means this printer is, well, it's pointing, if it's pointing it to the process, then it's like saying, who has the printer? And the printer has the name of that person who is pointing at it. So the printer is allocated. So these are the two words to use to read this diagram. And we'll be using those diagrams quite a lot. So to read it, you start from the tail, you name whatever it is. That's either a resource or a process. We only have processes and resources. So what does this mean? This arrow from P to a file. Anybody know? Process number 2 is pointing at the file. What does that mean? How would you read that? Needs is not really, okay, it's correct, but it's not the right word we use in this diagram. Request. So process number 2 is requesting the file. So we only have 2 words, either request or allocated. So you must use either of those 2 words, just so we'll all agree on the same terminology. And that's all there is. There's only, in fact, there are only 3 or 4 symbols. A process is always denoted by a circle. The user, this is the user that wants to use the resource. Anytime you see a circle, you know this is a user in our diagram. And usually resources are denoted by a square. So if you see a square, it's a resource. Whatever it is, it's a device that needs to be used, or something that needs to be used. Now, in this case, there are a number of conditions that are really important. This device is dedicated. And so is this file. So that means 2 people cannot, or 2 users cannot use them, either one of them simultaneously. So, and this is the first condition for a deadlock, if we are using dedicated resources. If these resources are shareable, well then there is no problem. What's a shareable resource? Do you remember? What's a shareable device? Say again, shared by more than 1 user? Can it be used by more than 1 user? Okay, simultaneously. I was going to say almost right. Okay, so these devices are not shareable. They are dedicated, which means they cannot be used by more than 1 user at a time. So if user 1 is using this file, then user 2 has to wait. That's the problem, is waiting. And also, this guy has the file allocated to it, but it needs a printer. The printer is not available. So user P1 has to wait. So both of them are sitting waiting. Now, is it possible that, for example, this guy needs the file and says, I need the printer, but the printer is someone else. Can we take it away from the other person or the other user? You know, in some systems, yes, we can. It depends. What do we call a system that will take a resource from you, interrupt you and take the resource from you? Anybody remembers the name? I can't hear you. Yeah, it sounds correct, but I can't hear you. What's a system that allows a resource to be, a process to be interrupted and we take the resource from it? Okay, does the word preemptive rings a bell? Or non-preemptive? What does it mean? What does preemptive system mean? We did, remember the policies, and we said some of them are preemptive policies. The shortest jump next. So if there are few processes and they need the processor for 5 milliseconds, 20 milliseconds, 100 milliseconds, we say use the shortest. Then you go for the shortest one, the 5 milliseconds, and give it the CPU. What if the moment we give the CPU, another processor arrived? So this one started using the CPU. In less than a second or millisecond, another processor said, I need the CPU for 2 seconds. Do we stop the one that has the CPU, interrupt and take the CPU from it because a shorter one came in, or not? It depends. Are we running a preemptive system or non-preemptive system? If it's non-preemptive, that means, no, sorry, you cannot interrupt somebody who was given a resource. Okay, before giving them the resource, we'll implement the rules, the shorter or the fastest or the higher priority. But once you get the resource, for example, you have medium priority. Somebody, after you got the CPU, somebody came and said, I have a higher priority, can you stop that? Well, it depends. If we are running a preemptive, yes, we will stop it. We'll take the resource from it and we give it to the one with the higher priority. But if it's non-preemptive, we say no. Once we give the resource, we do not interrupt any process until they finish with the resource. Okay? So, if we are, now this guy has a file and needs a printer. The printer is with this one. Can we interrupt this one? Well, it depends. If our system is non-preemptive, that means no, we cannot interrupt it. Before we gave it to it, maybe there's a policy who is higher priority or who is shorter, who is, quickest, whatever. But once it's given, we cannot take it away from it. So that's the second condition. If we can take the printer from this guy and give it to this one, then this guy will finish because it has the file and the printer. Sooner or later it'll finish. It'll finish in half a second or in a minute or 10 minutes. But sooner or later, if you have everything you need, then you will finish. So if this process got the file and the printer, then there'll be no deadlock because sooner or later until finish it will release both of them and this guy can get them and go and finish as well. So if we allow preemptiveness, if we allow a resource to be taken back and given to someone else, then we will never have deadlocks. Okay, so that's the second condition. If we have non-preemptive, then maybe there's a possibility we can have a deadlock. If we had preemptive, if we allow taking the resource from a process, then we will never have deadlocks. But of course, we cannot always allow preemptiveness. We cannot always take away resources. If you start printing on the printer 3 or 4 lines or half a page, we cannot come and take the printer and give it to someone else and they start printing on the same page. It doesn't work. And we realize with the race problem, we cannot give 2 programs or processes the same file to update. That can cause problems. So in some systems, we cannot do preemption. So if non-preemption, this is the second condition. Dedicated devices is the first condition. So in order to actually have a deadlock, we only have deadlocks if our devices are dedicated devices that we can never share. Because if you can share them, you don't have to wait. Just walk in, you share the same device. But unfortunately, if the device cannot allow more than one user, then the second user has to wait, and third user and fourth, they all have to wait in a queue. All right. So we have dedicated devices, we have non-preemptiveness, and if we have also something called a circular wait, is another condition that if we don't, as long maybe we have many users, but they're not really going in a circle. They might need different files and they never have to go into this circle. But, for example, we could say something else. We could say, all right, this guy here needs 2 devices. Ask for the first one, got it. Ask for the second one, it didn't get it. That's busy. We could implement a condition. We say, okay, if not all your resources that you need now, if they're not all available, then give up the first resource. And wait, don't start. So if we say to this guy, you asked for the file, you got it. You asked for the printer, you didn't get it. We suggest you should give up the file now. If that is the case, if we don't allow a process to have a resource and wait for another resource while holding this resource, if we say, no, you cannot hold it, release it until they're all available, then if this resource becomes free, then this guy here comes in, was the printer, and say, can I have the file? If it's free, then it'll get it, it will finish, it will release both of them, now that one can finish. You see the little trick? If we say, if you need 2 or 3 or 4 resources, you ask for them, you got some of them, but some of them are not available. Normally you should go and wait while you have the resources that you got. No, if we say release those resources, then we will never have a deadlock. So that condition, the one that causes the deadlock, that's not releasing, that's called hold and wait. If you're allowed to go into a waiting state, this guy got this resource, now it needs a second one, it's not available, it goes into waiting mode. If it's waiting while holding the first resource, that can be a problem. That is another step towards a lock. So as you can see now, we have 3 conditions, 3 steps. If we have 3 of them, like dedicated, if all our devices are dedicated, and if we implement the non-preemptive, that means if you have a resource, we will not interrupt you and take the resource from you. That means non-preemptive. That's what's implemented in our system. And if we allow a process to hold a resource and go waiting while holding that resource. Those 3 steps get us very close to having a deadlock. So it's going to happen. Sooner or later we're going to have a deadlock. All we need is for this to have the last and final condition, and that's a deadlock, and it's called circular wait. And what does a circular wait mean? It means that the processes, they form a circle. If you follow the allocation and requests of resources, it will bring you back to the same point. There could be 2 processes, could be 5 processes. If we keep following, how do we follow it? We say, this resource, who is it allocated to? Remember, we started here. It's allocated to this process. What does this, why is this process waiting? It's waiting on this resource. And who has that resource? This process. And why is this one waiting? It's waiting on this resource. Oh, we got to the same starting point. That's a circle. Even if it doesn't really take a circular shape, but if you follow it, bring it to the same point, we call it a circular weight. Then, what's a circular weight? It's multiple processes are in a waiting kind of sequence. They're waiting on each other. Each one of them has at least one resource, maybe more, and it's waiting on at least one more resource. But if you follow, there is a circle that brings you to the same point. That's a deadlock. So as you can see here, there are 4 deadlocks. If I say to you, how does a deadlock happen? The easiest and best answer to say, there are 4 conditions. If we have them in our system, if we have the 4 conditions, not one of them, the 4 conditions. Condition 1 and condition 2 and condition, not or. Those 4 conditions, if they all happen in a system, then there is a deadlock, or deadlock is going to happen. Right, what are these 4 conditions? The first condition is dedicated. They actually have another name for it. They call it mutual exclusion. That's just a fancy name. Mutual exclusion. What does mutual exclusion mean? It means a dedicated device. So that's the first condition, mutual exclusion, or a mutual exclusive device. If the devices we have are mutually exclusive, what does the word mutually exclusive? That means they can only be used by one person. It's like when I say something is exclusive to you, that means hey, you can relax. You're the only user. So if we give you a printer, say it's exclusively yours. That means you can use it for as long as you like. When you finish, then we might give it to another user. You go book a room in a hotel or a swimming pool, they can tell you this swimming pool is exclusively yours. That means no one else will come into this swimming pool. That's what mutual exclusive is. That's the first condition. Right. What does hold and wait mean? Anybody can explain what hold and wait means? Did you say something? Yeah, I think you did. Okay, try to explain it. What's hold and wait? What does it mean? What's this condition? In simple words. Anybody? Anybody knows how to explain hold and wait condition? Yeah, hold on, sorry, yeah?
When a process wants 2 resources at the same time.
Or more, yeah?
When a process wants 2 or more resources at the same time.
Yeah.
So he
No, that's not hold and wait on its own.
holds one and waits for the other.
Yeah, if a process has a resource, thank you, and it needs another resource, but the second resource is not available, you need to say that. So I need 2 resources. I got one, and I need the second one, but the second one is not available. Of course, I have to wait. But if I wait while holding on to the first resource, that's called hold and wait. I am allowed to hold a resource and wait for another one. If that's allowed in our system, then we're getting closer to a deadlock. What's the third condition? Non-preemptive. What does non-preemptive mean? Okay, explain it a bit more to me in this sense, in the deadlock sense. What does non-preemptive mean in this context? Like I have a resource and I want another one, but it's not free.
External interruptions, dysfunctions. Requires question.
Okay, anybody can put it in simpler words. Leave the interruptions now and processes running and all that.
We cannot get resources from process.
Say again?
We cannot get resources from process.
Yeah, okay. But in our deadlock sense here, similarly as this gentleman correctly described hold and wait, or defined it, also in non-preemptive, if I have a resource and I need another resource, but the other resource is held by someone else, can the system go and take it away from the other process if they cannot, that's what non-preemptive means. So the system cannot take a resource from a process that's already been allocated to it and give it to another one. That's not allowed. If it's not allowed, then we're getting even closer to a deadlock. That means somebody who is waiting will not be relieved, will not take the resource and give it to you to finish, and we allow you to hold the resource that you have, and all the resources are mutually exclusive, they cannot be shared. All that's happening, the last condition, once we get into a circle, sometimes we're lucky, we don't get into a circle, and we don't have a deadlock. Let's say you have a process, right? It needs a resource, or two resources. It has one, and now it needs the other one. It's not available, then it has to wait, because this one is held by another process, process 5, this is process 4, and this process, it has this resource, but it needs another one. It's pointing at another one, that means I need that one, but that one is already given to another process. And then this one is waiting for another resource, and that's held by another process. But it never goes in a circle, which means this process has all the resources needed to finish it, to release this one. Now this one can be given to this one. This process now it has all the resources it needs, and it will finish, it will release this resource and release this resource. Now this one can be given to this one. Now it has everything it needs. So unless we have a circular wait, if it's just one long chain of waiting but not circular, it's not a deadlock. It only becomes a deadlock if we get into a circle. If we can go back, follow those pointers, and they bring us back to the same point, that means it's a circular wait, and that's a deadlock. Okay, let me ask you another question, and then we leave deadlock for now, but we'll come back to it certainly. A deadlock, in order for a deadlock to happen, there are 4 conditions that must exist in a system. 4 conditions. Name one of them. What's?
Dedicated resource.
Pardon? One of them, just one.
A resource should be dedicated.
Resources are mutually exclusive. Is that what he said? Yeah, dedicated resources. They are not shareable resources. That's the first condition in a system. That means, hey, we can have a deadlock, but only if the other 3 are also in the system. In order to prevent and get rid of deadlocks, we never have a deadlock. If we need 4 conditions, condition 1 and condition 2 and condition 3 and condition 4. If we can remove one of those conditions from our system, then we will never have a deadlock. So it's very easy to solve, to prevent a deadlock in a system. If you are asked a question in an exam, how do you actually prevent a deadlock? You start by saying, okay, in order for a deadlock to happen, we need 4 conditions that they all must be in the system. If we can remove one of them, then we will never have a deadlock. So it's reasonably easy, but as you can see later, it's not that easy. But anyway, so that's the first condition. Mutual exclusive devices. Give me a second condition. Anybody there? Anybody with us? Yeah? Second condition for a deadlock to happen. Circular wait. That's the last condition, but yeah, I'll take that. Circular wait. So now we have mutual exclusion and circular wait. Any other condition?
Hold and wait and non.
Hold and wait. Thank you. Don't get me too simultaneous at the same time. That could be. What's the last condition? Well, they named 3. They named mutual exclusion, hold and wait, and okay, circular wait. Yeah, no, that they've already named circular wait. The 4th condition, the missing condition. Non-preemptive. What's non-preemptive? What does non-preemptive mean?
It's not interrupt.
You cannot interrupt another process, take the resource from it and maybe give it to another one. Okay. So these are the 4 conditions required to have a deadlock. How can we prevent a deadlock? Any idea how a deadlock can be prevented in a system that we will never have a deadlock? Are you with me, guys? Everybody not working on another assignment? By eliminating one of the conditions. Just eliminate this condition. condition. We're not going to have, in our system, we will not have dedicated devices. All our devices are shareable. That means you'll never have to wait. Any device you want, even if there are 2 users using it, you can use it. You don't have to wait. You don't have to wait. That means we'll never have a deadlock. Okay. We'll get into this in more detail, but if you understand the idea, the rest of it is easy, I hope. But you seem to get the main idea, so I'm glad. Just talk about the last item, which we will be talking about next week. The critical region, or the critical section. Again, this happens with another form of programming. The best, remember, just tell you about this form of programming. You probably have, I don't know, I don't think you have started programming that way. But imagine if this is our memory, and it's divided into, sections. So every program will get its own part. So that's program 1 is running there, maybe, or program 2, program 3, and so on. And another program you need to run, you need more memory. It will take more memory, and then memory will fill up. We don't have unlimited memory. Especially if those processes, they work together somehow. Like in a factory, you have a number of machines. One machine will do something, pass the thing in line to the next machine that will do something else, like manufacturing a car. Maybe one machine will make the frame, the other one fits the wheels, the other one fits the engine, the other one paints it, or something like that. So one does one job and passes it to the other. They started doing that in programming as well. So you can have multiple programs. This process is running, generating something, let's say a list of numbers, and then pass them to the next process. First, passing information to another process is a problem. In memory, if you have a program running or a process, you cannot communicate with the other process. Not internally, not in the system. Maybe one way to communicate, for a processor to communicate, I don't know if you got into that yet, but if a process, for example, writes to a file, we have a file, and one process kind of sends data or records or names or whatever, and you can run another process, so that's process 1, and process number 2 can open this file and read from it. And that's how processes can communicate together. One writes information to files and the other one reads them. But remember, a file is on a hard disk, which is very, very slow compared to the CPU, compared to those processes that are executed at almost lightning speed. So they'll not communicate efficiently together. And internally, they cannot communicate together because they do not share memory. No processes will share memory. So what they started doing, somebody came up with a brilliant idea that you can actually create a copy of a process. So those two processes, the two functions, put them in one program. So we have one process. Maybe you say, and it has functions. This is the function that will generate the list of names, and this process that will read those names, get the information. So one of them creates data, or whatever, numbers, and want to pass them to the other one. That's the way those two processes were working. But now, they got into something they called threading. processing. So what's that? A process can actually create another copy of itself or part of itself. But let's say just copy itself. So now you can copy get as many copies of the same process as you want. Right. So it's like we have two processes. One process, let's say you get to a point, it starts running, you say, okay, different languages have different commands to say, give me another thread, give me another copy of myself. In C, I think it's fork. But, you can find out what's in the language you're using. So it means it gives you another copy of itself, but it's actually over itself. It doesn't need more memory. That's the good thing about threads. You don't need more memory. It actually uses the same code. It's exactly like, for example, you have a recipe hung on the wall, how to make a cake. Step 1, do this. Step 2, do that. Step 3, that's a program. Any list of instructions is a program. But now, you can walk into the kitchen and start running this program. You do it yourself, implement it. Okay, take the eggs, break them, mix. And then you got to step number 4. Another friend walks into the kitchen and starts working on the same program, but they a separate, person. So you have 2 people now making the cake, but this one is at step 1, this one is step 4. And maybe after a little while, another person can come in, and so the program is not duplicated, but we have 3 users, 3 people doing the work. Same exactly here. You can get the same code, but you have multiple threads. Each one of those, we call it a thread. It's like a process. We call it a thread, so it actually came from the same copy of another existing process when you hear the word thread. So the program is in memory, and one is running, and then the second one comes running. So they're exactly the same. The only difference between them is the ID. Your ID is number 1, for example, or 478. Your ID, the second one is 479. So here you can say, if you are the first ID, we'll do this process, and if you're the ID number 2, jump to this process. So we have 2 processes running. It's like here, you say, okay, you're cooking the same cake, but listen, if you are the first person to walk in here, continue. If not, go to this step number 4. Maybe you're making a cake, but somebody's going to be specializing in icing. So you say, if you are the guy who's going to be doing icing, okay, jump to line number 20. And you start doing that. But they're all following the same code, but different parts of the code. So that's called threading. So threading is a new modern way, like it's been around for a couple of decades, but it's a new kind of way at the time for programming. Instead of running 2 separate processes, it's cheaper to run 2 threads, 2 copies of the same process. Because the main clear reason, memory. You don't have the code again in memory. So you can run more processes. Remember, when your memory fills, then that's it, you can't run anymore. With this one, you don't fill memory. You can run 10 processes of the same program. Or 10 threads of the same process. Okay, so it's a nice way of doing it. And what's good about this is that they all have, remember, at the start of every program, all the variables are there, X, Y, Z, all that. So they all have access to the same variables, and that's how they communicate. One of them puts the value X, puts a value in it, this guy goes and reads X. Remember, if you had separate programs, you cannot go and read from the memory of another program. But this memory, because now we are sharing exactly the same code and same place in memory, then we're also sharing the variables. And if we are sharing the variables, now we can communicate at lightning speed. This is the advantage of threading. So when you get to programming using threads or threading, you realize it's an extremely fast way of processes to talk to one another at lightning speed. And they can do that because they share the same memory and the same variables. Other normal processes, they are not even allowed to go near each other. They'll be terminated if you try to access someone else's memory. So now, look at it now. Imagine we have many, this is theoretically, now we have 3 threads of the same code running. It's like 3 processes, separate processes running, but they're not separate as such. Most of the time they realize there is no problem. They can all run, one is running here, the other one is running there, and then this guy might say, okay, loop back, go to the start. So they're all running the 3 processes, and each one thinks I am the only one running here. That's my code. In fact, it's not this code, they're following the same code. And generally, most of the time, there is no problem, but there are certain parts of code that they say, okay, this part of code, please do not run it at the same time. This part of code, it's the same in, remember, there's only 1 copy, but there's 3 running it. So I'm just showing the 3, what each one of them can see, but in fact, they're running the same code. But one of them could be executing at this line, the other one is executing this line, that one is executing at this line. So as long as they're on separate lines, there's no problem. On a lot of lines, there's no problem either. But as you can see also, sometimes in order, for example, if we have an array in memory, you know what an array is? Yeah? I think so. So they say sometimes this part of code can be dangerous if executed at the same time. And they call this the critical region of a program. Sometimes there might be 2 parts of the code of the same program that's dangerous. Don't run. If you get to this code, you can't have 2 or 3 processes actually executing that line. Other lines, it's no problem. They can execute even the same line. But in this region or that region, no. They can cause a problem. This is like in train stations or in train networks. Imagine if you have a train coming on this track, going this way, and another train coming from another city going to a different city, but they're sharing this track. This is like what we call the critical region in coding, in programming. So if a train comes this way and drives into this part, and another train meets it there, they could be a chaos, they could be a problem. So that's what we hear as well. We can have a problem if more than one program enters that critical section. So how do we prevent that? And we will look at a number of ways, but one of them is a simple signal that we can have, say, for example, we have a traffic light, red or green, or, okay, this train can see, and all trains coming from different directions, they cannot see one another, but they can see this signal. Is it red, the red light? I mean, don't go in, there's somebody on the track. Or, it's clear, it's green. And if you want to, for example, it's green, this is the way simply it works, we look at it in more details. If a train comes in from the side and looks at the light, says green, say, okay, it has a switch here on the track. Hit the switch and it goes red. Now it can keep moving. So the train is here. Another train comes in, approaches, you can see the red, it has stopped. That means somebody is on that track. That's very simple. Right. When this guy leaves, he hits the switch and this turns green. I mean, it's okay. This guy sees it. So, before it moves, there's a lever here. He hits the lever, turns it red. That means now I am going in there. If another train comes in, they see the red, they have to wait. So it's so simple. One switch. In fact, in computing, we have one bit. One little bit. We can say, let's just say, we call it, I don't know, we call it any name. Let's say we call it X. X is 0, if there's nobody in there. If you program and come in here and you find this is 0, that means this part of the code, it's free, no one is in it. You turn it into 1 and go in there. If someone else, see, the code is the same, X is here, it's common. So they can all see X. Was 0, now it's 1. Now the second process came in, which is really working here, but let's say it came in here and says, okay, I'm going to go into this section. First thing it checks X. Is it 0? Is it free? No, it's not. Well, then you have to wait. Check it again, check it again, check it again, until whoever is in there leaves, and the first thing here says, turn X to 0. So he goes and turns 0 off. Now this process goes, oh, that's not 1 anymore. Let me go in. First thing before you go in, turn X to 1. That's just like turning it red light to green light. That's very simple, very easy. One line of code that checks at the start. Is the critical section free? Yes, it is. Well, it's not anymore. Book it for me. This is like flying into your airplane, going home for your flight, and then you decide you need to go and visit the toilet. You go in there, but you have to first check that sign on the door. It says occupied. You say occupied, right, on airplanes, or free. So if it's free, you go in, but you make it occupied, so no one else will follow you. So it's so simple. If you forget to think of the toilet doors in an airplane, but so simple that you don't even have to get mixed in it. But there are 3 techniques that we will look at them in greater details. One of them has a problem, because just I'll tell you what the problem is very quickly, but we'll go through it next week. If this train comes in, looking at this light, let's say there are 2 trains coming in at the same time, and the light is green. It's like 2 programs coming in here, and the switch is 0. The variable here, X, is 0. They say, what variable is that? It's 0. It's great. Now, both trains drivers, they cannot see each other, but they can see the light green. They say, okay, there's nobody in the critical section. It's great. This guy hits the lever, that guy hits the lever at the same time. It's one of them gets there and turns the light into red. Each one of them thinks, I've just booked myself that. I turned the light red. This guy says, I turned that light red. Now then that track is mine, it's free. And they both go in at the same time, and sometimes they end up to having a crash. So we will look at this technique. There are actually 3 techniques that are used. We'll look at each one of them next week. But this is what we'll be doing this week and next week. So today, hopefully, we should be going through up to the deadlocks. And next week we'll look at the critical regions, and we'll look at what's known as semaphores. Any questions? No questions? Good. Now, are you with me? Give me one condition in order for a deadlock to happen. What conditions? There are 4 conditions that they must exist in a system. Name one of them. Non-preemptive. Can you tell me what non-preemptive is? I get the condition from one person, and the other person explain what it is.
If you cannot interrupt if a resource cannot be interrupted.
Yeah, well, maybe it's already asleep. It doesn't need to be interrupted. So what? What's non-preemptive really? It's not just the interruption, because sometimes that process is asleep, already interrupted.
So let's say the resource is blocked and notified immediately.
Okay. Anybody can tell me what's non-preemptive? What non-preemptive is? What's non-preemptive, guys? Anybody in the back? What does the non-preemptive condition mean? Not really, no. Yeah? A process cannot be taken away from a process. So it's the resource cannot be taken away from a process. The process may be interrupted if it's running, but even if it's not running, even if it's asleep, we interrupt it. But it's not, the purpose is not interrupting it, it's taking the resource from it. So non-preemptive, we cannot take the resource from a process. Okay, we cannot interrupt a process. If it's already interrupted, we cannot take the resource away from it until it gives it. That's what the non-preemptive mean. Do you get that? No? Get more sleep. Go to bed early. Okay, that's condition number 1. Condition number 2? Huh? Mutual exclusion. Who's going to tell me what mutual exclusion is? What's a mutual exclusive device? It is a dedicated device. What's a dedicated device?
You are the only user.
I am the only one who can use it, no one else can use it. What about you? Can you use that device? At the same time. Only one user can use this device. That's what mutual exclusion is. A device that can only be used by one user at a time. What's the third condition? So I can't remember it. Okay. Non-preemption and mutual exclusion. Hold and wait. Who can tell me what does hold and wait mean? You know what it means? Oh, no, thank you. Too much for you. That's too many problems. Yeah? Signore. Por favore. No? Anybody else on this side? What's hold and wait condition? What's hold and wait condition? Anybody? Okay, I'll say this one. Hold and wait means if you have a resource and you need another resource and that resource is not available, then you have to go and wait. If you are allowed to go waiting while you hold the resource that you have, you don't have to give it up. That means hold and wait. That's what the word hold and wait. You hold the resource that you have and you enter into a waiting state, waiting on another resource. If that's allowed, that's condition number 3. And finally, the last condition is circular wait. If we have a circular wait, then we have a deadlock. Okay, I talked about the race problem. The race problem is if you try to go to a file, read information and update it. And two processes try to do that at the same time, we have a problem and we end up with the wrong result. No errors, just wrong result. Like there's no, the operating system doesn't interrupt the program and say, sorry, you made a mistake. They make no mistakes. But the order in which they are doing stuff is wrong, and that will produce wrong results. So we can solve that problem. How is that problem solved? Anybody remembers how to solve the race problem? Using locks. Using a lock. That means, a lock means if you want to use a resource, the operating system will lock it on your behalf. You are the user. No one else can use it until you finish with it, and then release the lock. That means no two processes will use the same file, maybe, or the same device. That's one technique. But from the moment you say locking, that means we're starting, the others have to wait, and that leads to deadlocks. How do we prevent a deadlock in our system? We never have a deadlock. What is the approach of eliminating prevention? This is called deadlock prevention. How do we prevent a deadlock from happening? Anybody? Anybody? Thank you, Sakriya. Pardon? One of them. 4 conditions. By eliminating one of the 4 conditions that are required for a deadlock. Remember, a deadlock can only happen if we have 4 conditions. So if we can manage to remove one of those 4 conditions from our system, then we will never have a deadlock. This clock is not right, is it? I thought we kind of made a leap in time. All right, I'm going to stop this and we put the lecture notes on.